Good afternoon, everyone. This is my great honor to be here virtually to present my research at this conference. My name is Tom Tateno. I'm the second year of the PhD study at the Musashino University. And also I'm serving as a managing director of the Global Thermostat Japan. Let me share my screen with you. Today's presentation is geographical mapping and the knowledge-based indicative cost estimation for direct air capture CO2 utilization. Presentation overview and research overview. What I'm doing is solving a social problem, which is climate change, by CO2 removal and utilization by direct air capture, DAC, and the combinational optimization process and the key consideration are DAC location recommendation by distance calculation, and we have a constraint and a constraint item, and the balance of volume, and indicative cost estimation, and the project prioritization. This is an overview of my research. Introduction. We all know climate change must be urgently addressed 1.5 Celsius. Let me share the video clip of our business here.
Global Thermostat has developed a unique and powerful direct air capture solution to address climate change at its source and unlock massive, more sustainable industries. It's now clear we have emitted too much carbon dioxide into our atmosphere. We urgently need to remove billions of tons of this greenhouse gas to successfully address the climate challenge and rapidly replace fossil carbon with air carbon to power our economy.
Global Thermostat's patented direct air capture technology is the key to large-scale, low-cost carbon removal and the next industrial revolution. In simple terms, our solution works by using highly efficient fans to pass large volumes of air over high surface area contactors coated with a proprietary substance that naturally attracts CO2. We then use low-temperature heat to separate out the captured CO2 and repeat the process all over again.
And
let me start why I'm focusing on the DAC. And my career started in early 80s. Yes, I'm the old guy. And I used to work for the company named JGC, which is oil refinery and liquid natural gas EPC company. And I have assigned several locations. And gray dot is oil refinery. Some location you may be familiar with, Pearl Terminal, Chuchang, Singapore refinery in Geelong, and liquid natural gas Pearl Terminal, Alun Aceh, and Petronas Benso. And I was so happy to contribute to the economic development of these countries with fossil oil and gas resources. But after 40 years, I realized my plant I participate was source of the CO2 emission, which is also causing the climate change. As you may know, we have to remove the CO2 permanently from the air. And there are two types of the approach. One is CO2 reduction. Currently, 41 billion CO2 has been emitted. They has to be reduced. But in the meantime, we have to remove the CO2 already accumulated over the last 100 years. So my research is focused on the CO2 removal, means negative emissions. And in summary, CO2 reduction is needed and the CO2 removal, which is I'm focusing. And once CO2 removed from the air, there's a two approach. One is store under the ground permanently, or utilize the CO2 for other purposes. And this time, my research is using the construction material and agriculture, which is about $350 billion annual market, and agriculture with $25 billion market globally per year. And this is the application I'm currently focusing on. This is a reality check. And reality check 1.5 goal cannot be achieved at the current pace of the progress. That in 2023, we have only 10,000 tons captured from there, only 18 units globally. We need to capture 1 billion by 2030, and we capture 5 billion by 2050. It's really a great challenge. but data science can support the acceleration of DAC deployment. What is missing from current real world? Industry-specific practical data is not available. Easy to use tools and methods is not available. Data-driven justification has not been considered. In the micro and the local perspective, everyone talking about the global perspective and not micro and local perspective. And the balance of quantity consideration is not yet. And the sharing economy model is not yet. So my research is trying to combine all missing product as a solution. Research framework. This is the high-level graphical image. To operate the DAC to capture the CO2 from the air, we need electricity. And once we capture the CO2, we need to transport to the location where we are going to use or we are going to store. So these are the all players or this shows up on the supply chain. And my system framework, research framework is combinatorial optimization with various cost carbon intensity constraints. And with this consideration, we need to identify the suitable DAC siting location. We need to simulate the cost. And we need to provide the tools for the decision makers. And I use some case study, which is concrete and greenhouse cultivation. These two applications are widely spread globally. And reality is very small scale and many opportunities and low entry barrier to consider. And system architecture, on the right-hand side, this is data acquisitions. Very simple, where the CO2 concrete plants are located, where the solar PV and the wind generator is located. These are the input. And right-hand side is kind of knowledge transfer from the industrial knowledge into the parameter setting. And then knowledge integrative method conversion factor is created. And these two factors are combined together using computer and to do the distance calculation, cost estimation, and optimization, and cost sharing methodology, and output is be displayed on the screen. This is the whole picture of the system I'm going to present. And the final output is just like this. This is Tokyo metropolitan area. Let me explain one by one. Yellow dot is, this is the concrete companies located. And 1, 2, 3, 4, and everywhere. And each plant has a maximum capacity or requirement of CO2 25 ton each. And that itself in the 100-ton unit. So if we combine 1, 2, 3, 4 together, it's total 100 CO2 is needed, and we can put the one DAC somewhere. But where? Here, 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 or here. And all the distance calculation and the way the electricity should be, and everything has been calculated by combination or optimizations. And system can tell us where should priority number 1, number 2, and number 3. And each option has the detailed explanation about the logic why this location has been selected. This is the entire system architectures. And the process is acquire the location information, set a KPI by knowledge-based unified cost index. This is critical. And the constraint adjustment and the distance calculation by fossil-based penalty. If we use a fossil-based electricity, we need to add the penalty on that. Balance of quantity calculation, and of course, to operate the DAC, how much CO2 needed, how much electricity available, all kind of the balance of the quantity calculation needed. And also, I explained to you at the previous slide, cost sharing concept will be reality. And I all combined 1 to 6 together within a concept of the dynamic programming and the genetic algorithm for the optimization. And I created some kind of the self-made algorithm for this proof of concept. And input data is just like this. And key KPI, knowledge-based transfer for the cost estimation and capital cost, electricity cost, and basically translated into the dollar per CO2 ton. And total formula, it will be sum of the capex, linear electricity cost, distance cost, infrastructure cost, cost-based CO2 penalty, and summing together, making the one single unified cost per ton CO2. And the knowledge, it comes from the table. This is industrial knowledge. let's say how much the capex is required, and had $6.45, and this came from the industry database. And we picked 1, 2, 3, 4, 5 critical items as the key indicators to determine the cost per ton. And this data is translated into the parameter setting on the screen. Let's go to the practical model. This is Tokyo metropolitan area. You can see the yellow dot. This is the location the concrete plant is located. Green is solar power generators or wind generators located. And fossil-based energy is here. Now we are going to put the DAC. How many DAC is we can put? How much CO2 we can capture? What's the best way, most economical way to put the DAC in this region? This is the puzzle we need to solve. And there's some logic is needed. Let's say here's electricity, solar panel is here, and the concrete plant is here. If we put the DAC on the concrete plant, then costs will be electricity costs and plant costs only. But if we use fossil-based electricity, we need to be penalized because we are emitting the CO2 by fossil-based electricity. So this is the penalty will be applied. The same formula, if we put the DAC at the solar panel or wind generators, looks great. But we capture CO2, and the captured CO2 need to be transported, to this location. So we need a cost for the transportation. So all kinds of the element is combined together and calculate the optimized solutions. And the group session, as I explained to you before, let's say 20 ton plant, 30 ton plant, 40 ton plant, where to put the DAC? Yes, altogether 100 is the match to the 100 ton DAC capacity, this one. But put here, or put here. It depends on the location and the cost factor will be involved. So the whole algorithm, or just like a combination optimization, is making this grouping together. And experiment. And here is a chart, and you can see I put the location, central location. I want to see the 50 kilometer radius where the duct should be, and they can tell us where the duct to be located. And cost to be $1,278.39. And what's the next? And next to be here, and that should be moving from here to here. What's the number 3? That should be here, and number 4 is here. And of course, all costs is sorted and they're showing the result on the screen. If I move the radius to this location, and so the output is different. And in case of the greenhouse cultivation, it's totally different setup. And altogether, we can see this way. So result and conclusion, yes, I actually complete the system by identifying one location. And the functionality accuracy was verified. And this can be expanded to global scale and to be applied for other CCU. In the future research, I want to expand. This is the area of my research. And I want to add future projection by learning by doing method, which has been applied to the solar panel. And once I created and completed that mechanism, I want to apply for another net negative emission technologies such as afforestation and weathering and BECCS. And this is sample of the solar panel, the projection curve learning by doing. And this is my research. And thank you very much for your time and for your attention. I'm more than happy to take any question and constructive criticism from this point. Again, thank you very much.